Hello scholars, welcome. Mr. Hinkle here. Today we are talking about the Earth as a system. A system is a set of interrelated parts that all work together to form a whole. And our Earth is one big system with many, many subsystems working together. And how they interact is the purpose of this lecture. So we will discuss the Earth spheres interacting through forcings, feedbacks, sinks, and tipping points. Let's start here with the Earth system. So if we look at the Earth system, we can break it down into interacting parts, yes. And these interacting parts we will identify as Earth's spheres. We have the lithosphere, which is Earth's rock, the hydrosphere, which is Earth's water, the atmosphere, Earth's air, and something very near and dear to you and I, life, the biosphere. Now, depending on what text or what you're studying, you may even see part of the hydrosphere as the cryosphere because of the importance of frozen ice on the Earth system. And it's possible that you may even see the anthroposphere because of the significant impact that human beings have on the Earth. So these are the basic four: the lithosphere, hydrosphere, atmosphere, biosphere, possibly the cryosphere to subdivide a little bit more, and the anthroposphere. So everything we know about the physical world we live in occurs within these four spheres: the air, the water, the life, and the rock. And we study these four spheres independently and then even go deeper and deeper to separate individual components of these subsystems. Because to think about the entire Earth system as a whole, very complex. To focus in narrower and narrower and narrower allows us to develop an understanding on that very specific topic and then include that in our greater holistic understanding. So these are our four spheres, and they're not isolated. They work together. And the ways that they work together is the purpose of this lecture. Events create forcings and feedbacks, sinks, and tipping points. Here we can see all of it happening. We see our spheres: air, water, earth, life, and the movement of materials, the recycling of matter. So how we have movement from one sphere to another is the purpose, occurring through forcings, feedbacks, sinks, and tipping points. Okay, let's get into it. A forcing is an event. It is something that happens that moves a system away from an equilibrium. Equilibrium trying to be a steady state condition that a system is working towards. Equilibrium is dynamic because it's ever changing, but there is a baseline of equilibrium that systems tend towards. When an external event pushes that event or that equilibrium in a certain direction, this is called a forcing, aka forcing event. Okay, so we've got Earth systems. Now we're looking at Earth's systems interactions, and we are talking about forcing events. Moving a system away from equilibrium. After a forcing event occurs, there's going to be a response, and that response is going to be a feedback. Now, feedbacks can happen in one of two directions. It can be positive or negative. For example, the environment in this room gets very, very cold. The forcing event is cold. My body temperature gets cold, and in response, I put on a coat to get warm. That would be a negative feedback because it's in the opposite direction of the response. Feedback, opposite of response. A snowball goes downhill, and the further down it goes, the more snow it collects, the bigger it gets. The bigger it gets, the faster it goes, the more snow it collects. The more snow it collects, the bigger it gets. The bigger it gets, the more snow it collects, so on and so forth. The response and the stimulus are in the same direction. So positive and negative feedbacks can accelerate or slow down the changes occurring within a system. Let's look at an example, a volcanic eruption. So volcanoes are magnificent features of Earth's surface, and they erupt. Sometimes they explode, and sometimes they very gently let go of some lava. But for an explosive volcano, a pyroclastic explosion, ash and rock are blasted into the atmosphere. Gases are emitted into the atmosphere. Possible that some lava is running down slope. You can have a superheated mass of ash, gas, and dust pushing down slope at great velocity. That's called a pyroclastic flow. Let's see, I'm doing a lot of reaching here. If that mountain has ice or snow on it, the ash and gas will mix, that was funny, with the water and create a lahar or a mud flow, and then the flora and fauna in the immediate vicinity may be killed through this volcanic eruption. So this one volcanic eruption, all of these changes are occurring. This is the forcing event. In response, we have feedbacks in the atmosphere, in the ice, in ocean circulation, even in vegetation in the carbon cycle. So volcanoes erupt, and they increase the amount of particles in the atmosphere that scatters the sun's light. That scattering, due to the aerosols, causes more snow and ice to occur on the surface of the Earth, so increased ice albedo effect, which leads to further cooling that upsets global ocean circulation patterns because the oceans transport heat. They're a great moderator of climate by transporting heat. And this decrease, this cooling, leads to less available sunlight and lower temperatures, reducing photosynthesis, increasing CO2. All of that from volcanic eruptions. Now, every forcing event causes feedback events. That is why the Earth system is a dynamic, ever-changing place where we have constant inputs and responses happening. Mount Tambora explosion, 1815 in Indonesia. The following year was considered the year without a summer because the aerosols blocked the sun, leading to global cooling, which led to extreme weather events and an agricultural disaster. Forcing event, volcanic eruption. Feedback, extreme weather, agriculture is impacted, sunlight is blocked. Feedbacks and forcings. Now, where matter and energy are in a system, the location where these materials are stored is going to be called a sink. Let's take carbon dioxide, for example. Carbon dioxide is in the atmosphere, CO2, CH4. It's in the oceans as dissolved carbon in the shells of marine phytoplankton. This carbon lithifies into rocks, which are trapped in the rock record for very long periods of time. There's carbon in the biomass on Earth's surface. There's carbon in the soil. There's fossil carbon as fossil fuels. So all of these places are considered sinks. In the case of carbon, they are all considered carbon sinks. And it's important to think about where are matter and energy stored in which sphere. So I went through and I labeled or I identified the atmosphere, carbon sink, the hydrosphere, carbon sink, the biosphere, carbon sink, the lithosphere, carbon sink. And how much of these materials are available or present and what is the residence time? How long does a material remain in that location? So keywords here. Something to note one thing that we really want to tune into is what's considered a tipping point. And it's how large of a perturbation the forcing event occurs. In most cases, you have an equilibrium and a forcing event takes it away, and then the feedbacks in response will occur in the other spheres, but the responses will ultimately lead towards that event finding equilibrium. Well, at some point, the forcing event might be so great that there's no reversing it, that it creates a new equilibrium, a new normal, which is not good for species and habitats that have evolved to the current conditions on Earth. We see the big thing here that we're talking about, of course, spoiler, is climate change and how climate change affects the Earth system through all of Earth's spheres. And have we reached a critical tipping point in Earth's carbon dioxide? But it doesn't just happen. It can happen in weather, it can happen in ice, it can happen in monsoons, it can happen in vegetation. There are tipping points all over the world. Let's use the Atlantic Meridional Overturning Circulation, also known as the AMOC, which is a major component of Earth's climate system, and it's an area where ocean circulation becomes very salty and very cold, and cold salty water sinks, leading to deep water formation. So if here's the ocean, here's Greenland, and we have deep water formation, bottom of the ocean, where you have cold, salty water descending down into the deep ocean. Now, this is called thermohaline circulation, the global conveyor belt of Earth's water connecting surface ocean currents with deep ocean currents. The caution here resides in, well, if the Earth gets hotter because of climate change, then the ice caps on Greenland melt. The ice caps on Greenland melt, it dilutes the water here in the North Atlantic. The Earth gets hotter, more ice melts, more dilution, and all of a sudden we don't have salty water. And the fear of some scientists is that if the AMOC shuts off, if it reaches a critical point where the amount of fresh water that's being input into the system shuts down deep water formation, then that will have effects on the entire global ocean circulation patterns. So the AMOC is something that is studied very closely, that we're monitoring, and it is a great example of a tipping point. We haven't reached it yet, and we're hoping that we don't, but for example, this is a tipping point that we do not want to reach. Okay, let's bring it all together using climate change again. So complex processes, a complex Earth system. One second. Pardon me, I apologize. Complex processes are displayed on models known as causal loop diagrams. So you have inputs, right? You have the center here, global temperature, and all of the inputs and all of the forcings and all of the processes, the interactions that are happening to understand this system. Climate change is often considered to be Earth's temperature increasing. And while the average temperature of the Earth is rising, it is a much more complex problem than that. That's why global warming is kind of out. It's old news. Global climate change is in because of the complex interactions of Earth's spheres, from the pumping of fossil fuels in the lithosphere to increase greenhouse gases in the atmosphere, whoop, down here. The absorption of those gases causing the chemistry of the oceans to become more acidic in the hydrosphere, the melting of the ice in the cryosphere, and the impacts in the loss of life in the biosphere, all tied together through the anthroposphere. So temperature, climate change, is a great example of a complex process that occurs through all of Earth's systems that can be mapped using models known as causal loop diagrams. In conclusion, The Earth is a system, a set of interacting parts working together to form a whole. The atmosphere, Earth's air, the hydrosphere, Earth's water, the geosphere or lithosphere, Earth's rock, and the biosphere, Earth's life. And these spheres interact with each other through forcing events that lead to feedbacks, through the locations and the time of storing matter and energy in sinks, and through perturbations that will offset a system so much that it creates a new normal, a new equilibrium called tipping points. Thank you so much, and I will see you again.